In this webinar, researchers will share new approaches to smarter routing and vehicle technology that can cut energy use and reduce emissions. I'm pleased to welcome today's speakers. Professor Songshuan Sun is a professor in the Department of Mechanical Engineering at the University of Minnesota, and Michael Levin is an associate professor in the Department of Civil, Environmental, and Geoengineering at the University of Minnesota and a Center for Transportation Studies scholar. Sean Juan and Michael, I turn the webinar over to you. We're going to start with Song Xuan.
Yeah, well, thank you, Mauricio. Thank you for the introduction. So let me share my slides. Okay. So good afternoon. Again, it's a great to have the opportunity with the CTS webinar to share with you some of the work we have done related to transportation energy. So Mauricio obviously already talked about the importance in this area. So this is the outline of the presentation, 30 minutes. First, I'd like to talk about the motivations and background and motivations. Then I go through a couple of specific projects we work on with my students. Okay. So first, again, why transportation energy is important? Well, first of all, it accounts about 30% of the national energy consumption. So if people are familiar with the US national energy consumption, we consume about 100 quadrillion BTUs per year. Okay, quadrillion BTUs. British thermal unit. Okay, so that's the amount of energy we consume as a nation every year. About 30% of that is in transportation. And what's unique about transportation is comparing the other two big ones are commercial and residential buildings and industry, industrial plants. Okay. Comparing with the other sectors, what's unique about transportation is we have to carry energy on board. Okay, so basically all the cars running on road, we have to bring our own energy because we are mobile application. Okay, that immediately makes it a challenging issue. You have to be able to bring enough energy on board, and you have to be able to convert that energy in real time efficiently to propel the vehicle. Right? That's essentially the main, I would say, the main job of the auto manufacturers. Right? When you make a car, essentially you have to be able to bring the carry the energy and converting the energy to propel the vehicles. But there are two factors. Making a good car is only at most half of the story. So what are the two factors that affect, in my opinion, the transportation energy? The first one is the vehicle operation, which essentially I call power demand at every time instant, okay, every 1 second, depending on the speed and acceleration of your car, there is a power demand there you are asking your car to produce to propel your car, essentially maintain your motion. Right? How many kilowatts? Can be 10 kilowatts, can be 30 kilowatts, can be 100 kilowatts. When you try to merge on the highway, you step on the gas pedal, you try to get to a higher speed, you might ask for 60, 70 kilowatts. So when you are cruising on highway, you might only need 10 kilowatts. Okay, at every time instant, when you are driving, you are essentially demanding a power from the vehicle to maintain your motion. So that's I call power demand. So what are the factors that affect the power demand? Why do we need to have 10 kilowatts this time, 20 kilowatts that time? What is the determining factor? The factors are mainly two: traffic. Right? We can't just drive any way we want. We have to follow the traffic. And we have to follow the traffic rules. So So that's probably I would say the most important constraint on how we use the roadway, right? You get on the road, you find there are many people around you, especially in the rush hour. So you have to follow the traffic. You have to work with others. The second is within the degree of freedom you do have as an individual driver, well, then it's up to your behavior. Everybody drive differently. So the driver behavior also affect the power demand we are asking the vehicle to produce to maintain the motion. So those are the two factors, which really is not determined by the manufacturer of the vehicle. Right? You can have the same car, but you can have quite different drivers. You can have quite different traffic. And the second factor, of course, is the vehicle powertrain. It's basically the point is when you demand a power from the vehicle, who is producing that power? Somebody has to. But that is the vehicle powertrain. That is where your stored energy, either in liquid fuel, such as gasoline, or renewable fuel, or electricity from the battery, which are energy, then converted into mechanical motion that turns your wheel. Right? So that there is an energy storage, there is an energy conversion process, and that system, which does all the above, is called a powertrain system. And that obviously is done by the vehicle manufacturer. That I call vehicle design and control. How you design the vehicle, what kind of powertrain do you have? How do you control that powertrain? The powertrain has to be controlled independent. It is an internal combustion engine-based powertrain, or it is a electrical powertrain. They have to be controlled in real time. Here, this control is now the driver behavior. Even a driver is fixed. Okay, when they demand certain power, the electrical motor has to turn at a certain speed to deliver that power. So that's what I call the vehicle design control. Okay, so historically, as many of you know, those two, I would say, very important factors are completely separated. In fact, that's a good reason for that. Okay, because if you are the automotive OEM, how would you know everyday traffic? It's impossible to know, what kind of traffic you'll face today or tomorrow, and even it's not that easy to take that into consideration while you design the vehicle. What they do take into consideration, as you may know that in our nation, how do we test fuel economy? How do we test emissions? You go to the dealership, you see the sticker on the window. How many miles per gallon? How was that tested? It was tested against the so-called Federal Testing Procedure, FTP cycles. Well, they specify a local driving cycle and a highway driving cycle. So those are the standard driving cycles that are being used to evaluate the vehicle fuel economy as well as emissions. Of course, we know in real life, those two cycles cannot represent millions of vehicles, how they're being used on a daily basis. Okay, so as far as I know, historically, there was not much a tighter integration between these two factors, although they intrinsically affect energy consumption. In fact, I just do not see how can you separate them. One is power demand, the other one is power generation. Okay, so that's really is the issue. So my overall message is I think there will be a lot of opportunities if we can better or seamlessly integrate those two factors. Okay, so a little bit further argument along that line, and then people ask, well, sounds good. How do you actually integrate traffic and vehicle? Okay, how do you do that? Well, you do that by leveraging two emerging technologies. Those are relatively new, not brand new today, but relatively new. One is connectivity, the other one is automation. We didn't have, well, even connectivity today is now widely commercialized. Automation, we have some commercialized already, okay, but not, I wouldn't say widely commercialized, okay. So connectivity gave us real-time traffic information that including information about other vehicles as well as infrastructure. right? Such as signal phase and timing. So it's not just about, when we talk about traffic, it's not just about other cars. It's about infrastructure as well, because infrastructure controls, influence the vehicle operation as well as the traffic. So then this information, the information you collected through connectivity, essentially communication with other vehicles, with the infrastructure, provides you rich information where if you use them properly, smartly, you can actually anticipate future driving conditions. Basically means you can anticipate traffic in front of you in future, not too long a future, but at least in 10 to 15 seconds. Okay. So with then the next factor comes in is I call partial or full vehicle automation. Okay. So essentially, rather than to have a human 100% control the vehicle operation, which we talk about the driver behavior, computers drive the car. Okay, human is out. Of course, you will notice that in my presentation, when we refer to automation, we refer to the full spectrum of automation. We could have a driver assist system. So human is still here. Humans still drive the car, but we assist them. Okay, then partial automation. Maybe we take over the drive just for longitudinal drive, right? Like adaptive cruise control, right? But if you want to change the lane, if you want to do all the other fancy stuff, you still have to do it yourself. So partial automation. Of course, there is a full automation, right? So then the computer takes over the whole driving function. So when I talk about vehicle automation, I refer to the whole thing because you don't have to have full automation. You can already have benefit. And of course, with those two factors together, I think we have a strong opportunity to address the issues I mentioned in the previous slide. Okay, so continue on that. So how do you actually bring this idea into actual implementation? How do you put this on the ground? How do you put this in the vehicle? How do you put this in the infrastructure to actually see the real benefit? How do we do that? So my group has worked on this for, I would say, probably 15 years now. So we actually are using the so-called optimal control framework. Okay, so we essentially treat the traffic as a constraint. Okay, as I said, you can't just drive any way you want. You have to follow the traffic flow. So we actually proactively predict the traffic. Then we use that as a constraint to our optimization control problem. And then on the energy saving side, on individual vehicles, it can be saved at two levels. One is the vehicle level, essentially that determine the acceleration, the speed, which is your power demand. Okay. And the second level is the powertrain levels. Even for the same power demand, you can operate your powertrain smartly, and therefore you have a higher efficiency. Okay, so even your output exact the same amount of 10 kilowatts, but you are much more efficient in delivering this 10 kilowatts. Okay, so I talked about both already. So now let me show you what I meant on the powertrain level. So the powertrain level, those are three different type powertrains. You can buy all of them today on the market. I would say the conventional one is, which is still dominant one, is the internal combustion engine with automatic transmission. So that is still the dominant powertrain architecture in America. The second one is hybrid electric vehicle. The third one is electrical vehicle. Okay, so different powertrains. I'm not going into the details about the powertrain architecture, which is the primary research area of mine. But the bottom line is for the same power demand, okay, let's say one driver is driving testing drive one car one day per day. So they are driving all kind of powertrain architecture. Okay, so they are demanding exactly the same power demand. How would you use all different powertrain architecture to satisfy this driver's demand efficiently? So you have to essentially control those powertrains in real time. Okay, then the question would be, oh, what do I control? Which I talk about in the following slide. But the bottom line is, again, you have vehicle level optimization. Okay, essentially the speed and acceleration. and you also have a powertrain level optimization. Is how do I produce power efficiently to satisfy the power demand? And both have to be connected to the real-time traffic and infrastructure. Only then you have maximized your opportunity for saving energy. Okay, one question people always have when I talk about predicting traffic, they say, well, how can you predict traffic? Because now, even you have a CV technology, not everybody is going to talk to you. And many existing vehicles, they have no way of predicting, they have no communication device. What do you do? So we recognize the fact, no matter how we introduce a new technology, connectivity or automation, we're going to face mixed traffic scenario, which means it takes time for the technology to penetrate the market, right? So we're not going to have 100% CVs. We're not going to have 100% automated vehicles in anytime soon. Okay, so there will be a market percentage. So how do you do that? So not everybody talks to you. You say, oh, I collect information, therefore I can predict the traffic, but they don't talk to you. What do you do? Well, you can still predict traffic with limited information. Okay, you don't have to have everybody talk to you. You don't have to know every individual vehicle information. And therefore, we are using the traffic flow theory. We're working with Michael, treating the traffic as a fluid. Okay, then it become a continuum where you actually do not need to know individual vehicles. Okay, only you need to know information at certain points. Then you use that and physical law to synthesize the dynamics of the traffic. Okay, so that's the basic idea on this slides, because this is a real issue. If you see the only way for me to predicting traffic is everybody talk to me. I know everybody's information. Well, that's impossible. You simply, first of all, you can't. They don't talk to you. Second of all, even they do, you just don't have time to process all the information. It's too much information, right? You only need some information for the cars in front of you, maybe 100 to 300 meter also, because all you talk about is 10 to 15 seconds. Okay, you don't need to know a whole lot all the other stuff, and even your computer will not be fast enough to process. So let me now run through a couple examples. I know I spent a bunch of time on background because that was intentional, because I want to make sure people at least understand my rationale, okay? And when I go to the specific project, I will run a bit faster, okay? Because some of those are a little bit technical, so I'd be happy to answer questions or even follow up. So I have to go a bit faster because I got four examples here, okay? So the first one is actually a test bed. So this was funded by Federal Highway Administration as well as MnDOT. So the whole idea was, testing all those stuff, all this technology on road is not that easy, and also precisely measuring fuel economy and emissions is not easy. Okay, so we actually have very precise fuel measurement as well as the emission measurement instrument in our laboratory, and therefore the whole idea is, can we have a hardware in the loop test bed? Essentially, the engine is real, so the engine is 100% real, same as what inside the car, but we have a hydrostatic dyno showing here on the left-hand side that actually load the engine as if it is driving a real vehicle. Okay, because the engine doesn't know it's in a car or it's in a test cell. All it knows is what speed I'm driving and what torque I'm outputting. And so we are controlling a transient dynamometer so that to load the engine so that the engine thinks it is driving a real vehicle. So how do we do that? We have to model the vehicle. We have to model the vehicle resistance, okay, in real time as if it is driving in real traffic, and we then deliver that resistance, again, torque at certain speed to the engine through the hydrostatic dynamometer. Okay, so that's the basic idea. So with that, the same engine, GM 3.6 LFX engine, it was in a Cadillac SRX. That was the car. So we did that, and we obviously could had information data from the vehicle, and we use that to calibrate the model to make sure they actually match. So here you can see the result the result between what we did and what the vehicle did, you can see the benefits are very, very much similar. One is 11.3% eco drive versus baseline. Our testing results suggesting eco drive give you 10.6% benefit. So you can see they are pretty much matching very well. So that was the objective to see, can you evaluate all kinds of energy saving method technologies on the vehicle in the test cell, okay, without actually going to every single vehicle. Again, going to every single vehicle is costly, and there are also safety concerns. Okay, so that was the motivation for this project. Essentially, is a test bed to test energy saving technologies inside the laboratory with precise fuel economy and emissions measurement. So we also did living laboratory. Living laboratory basically means you get cars driving on the real road, okay? And you also talk to the signal controller. So here you can see the signal controller on Highway 55. Here you can see all the testing vehicles. So this way you bring real traffic data into the laboratory, okay? So what we do is the last car here, the green, is a fictitious car. It's not a real car. And this car is actually the test cell. It's a virtual vehicle inside the test cell, because we get all the information about all the cars in front of this fictitious car through communication. Okay, so all the other cars are real cars. The signal, of course, is real, but this one is virtual, and as if we are following the other cars. Okay, and therefore we can collect information, signal phase and timing information. We can have other vehicles information. Based on that, we predict the traffic, and based on that, we control our own vehicle motion. We also control our own powertrain operation. Then we see how much energy can we save. Okay, so this is a safe way to testing all kind of methodology. Okay, so now let me show you 3 different types of powertrain we tested. Okay, the first one, the conventional one, internal combustion engine. Here shows the engine map. I won't go into the details. I'm not sure people are familiar with the engine map. Essentially show the energy consumption as a function of speed and torque. Okay, so that's the engine map. And on the right-hand side, that is a transmission shift schedule. So what is the biggest factor that affect a conventional car? A conventional car refer to the internal combustion engine with the automatic transmission. Okay, that is still, as we speak, the predominant powertrain in America. Okay, what is the one big factor once the car has been manufactured that we can change efficiency, we can improve efficiency when this car is being used in real traffic? It is the following factor. It's by selecting the best gear position. Here I'm showing you a 6-speed transmission. If you go to the dealership today, they get 8-speed, 9-speed, 10-speed. Okay, many speeds. Okay, so but the question is, how do you know which gear to use? Well, you might wondering, well, didn't the manufacturer already determine how to use the gear? Of course they did, which is the graph on the right-hand side. They call shift schedule, which determine which gear to use depending on the vehicle speed and throttle position. But that map is calibrated before the vehicle was sold to you. It knows nothing about the traffic. Okay, it does not know how you're going to use it. If you actually know the traffic in front of you, you can actually optimize the gear position and therefore gain even better fuel economy. That's the basic idea. Okay, so with that, let me show you the framework we had. So essentially, again, we have traffic and traffic signal. We send that to the so-called traffic estimation. Then we run a real-time optimal control, which controls the vehicle. Okay, so that's how you close the loop. That's how you integrating traffic with vehicle operation as well as with powertrain control. And that, in my domain, they gave it a name called model predictive control. Means you are predicting future, okay, with the model and to determine your control. I'm not going to the details on how these things are done. We wrote a bunch of papers. If you are interested, I'm happy to share the papers to you with all the technical details. Okay, so essentially here shows you the details about traffic prediction. Like I said, you put those the roadway in front of you as cells, and there are cars into it, as I said, the beauty of this approach is you don't have to know information in all the cells. For example, here, this orange car is not connected. It doesn't even talk to you. In fact, you do not even know this car is there. Okay, you don't even know. You only know, well, there is a car when people talk to you, but that's fine because we treat this as a continuum fluids. Okay, by doing so that you don't have to know each cell information. Okay, so that's the traffic prediction part. I'm not going to the detailed series, but just to show you, here, again, this is the overall architecture. You see, we get the signal, we get real cars, we get this dyno, so we can close the loop. Okay. Maybe I just run a small video here. So the screen vehicle is the one that is controlled by us, as you can see, because the signal ahead of you is red, so it intentionally slows down. You can see the spacing between this vehicle and the preceding vehicle is getting bigger as it approaches the intersection, because it knows it's red. There's no way you can pass it. Okay. By doing so, it reduces time here for idling, because as soon as this vehicle arrives at the intersection, the signal turns green, so the vehicle can get going. Okay, so that's an obvious strategy you can do if you actually know signal phase and timing. Okay, so this example shows that, and here shows what we got from the test bed in the test cell. So the engine was driving as if it is on Highway 55, as if it is approaching Venetica, that intersection. Okay, so all the fuel economy, all the emissions data have been recorded in real time. Everything has been recorded. Okay. So now let me move on to the hybrid electric vehicle. So what do we do if we have a hybrid electric vehicle? The one I just talked about was an internal combustion engine with automatic transmission. Now we have let's say we have a hybrid electric, which you have an engine, you also have a battery. So this architecture, I'm not sure people familiar with, is called the power split hybrid. This is probably the most, I would say, advanced hybrid architecture that in commercial production. So Toyota Prius first introduced this architecture around 2000, 25 years ago, when Toyota hybrid entered the US market. Okay, so essentially they have a planetary gear set. The engine is connected to the carrier, the sun gear is connected to the generator, and the ring gear is connected to the output. Okay, and of course your generator and your motor are connected to your battery. And by doing so, you can split your power, the power from the engine, through the so-called mechanical path, basically mechanically going to the wheels, or electrical path. Basically, part of the engine energy is being converted into electricity by the generator. Then that electricity is used to propel the motor back to mechanical motion. That's why it's called power split hybrid transmission. Okay, so that's a hybrid architecture. You have the battery here, and with this extra degree of freedom of battery, now at every time instant, you can determine as your car moving forward. I said you need a power demand. You can then determine how much power do I want to get from the engine, how much do I want to get from the battery. Okay, so you can determine that. So you have two choices. Okay, you can split between the engine and the battery. So that gave you an extra degree of freedom, which you wouldn't have with the conventional powertrain, which you only have the engine. Okay, and here shows you the research we did. Again, you can do all the traffic prediction, and with the prediction, you can optimize how you want to drive on the vehicle level. Then you go to the powertrain level. At the powertrain level, you can determine how much you want to get from the engine, how much you want to get from the battery. Then you deliver the whole thing to the vehicle powertrain. Okay, so that's essentially is the idea. Okay, and here it shows you that if you only do powertrain optimization, okay, which basically means you do not do anything at the vehicle level. You just assume a human is driving it. This human is just an average driver. It doesn't improve any driving behavior. Okay, you only do powertrain. You only basically means optimize how the hybrid powertrain is being used. You get 10%. But if you only do the speed optimization, basically means you have a fully automated vehicle. Okay, so you take out the human, you know when to accelerate, when to decelerate, you get 17%. But if you do them together, you get 22.76%. Okay, so that's kind of the benefit we found. Last topic, electrical vehicle. So electrical vehicle, obviously, you do not have an internal combustion engine. All you have is a battery, inverter, and electrical motor, and go to the wheels of the vehicle. Okay, so that's what you get. And by the way, in this specific presentation, I show you with a fixed final drive, which is the most typical arrangement in today's EV you buy on market. However, there are few EVs, they actually have more than one gear after the motor. Okay, so you can have 2-speed or 3-speed transmission, even for EV. In fact, my students has done work with a multi-speed electrical vehicle study. So if you're interested, I'd be happy to talk to you as well. So if you have that, you also have to make a decision about which gear you are in for the EV at every time instant. Okay, that also has significant energy implications. So here, but you have a fixed gear, but still, when you drive at different speed, because the gear is fixed, so your electrical motor speed is determined as soon as your vehicle speed is determined. But your electrical motor efficiency, though, depending on the speed and load. And therefore, we have to bring in the efficiency map of the motor as well as the efficiency of the battery into the consideration when we optimize the overall vehicle efficiency. Okay, so that's a key consideration here. The other one is regenerative braking. With the electrical vehicle, you can have regen. Okay, and that regen essentially means as you slow down, rather than using a mechanical brake to burn out all the kinetic energy, you actually convert that into electrical energy. Okay, you want to maximize your regen. And here shows you the data we actually did. And I think I use this is probably a better chart to show you, what happens with the baseline or with the optimized vehicle. Okay, you can see all the energy flow from the battery coming out, how much you lost in the battery internal loss, how much you lost on the motor, and when they go to vehicle, how much is actually propelling the vehicle, how much is due to the friction braking, how much is being regen. Going back to the battery. So you can see, but the bottom line is with the optimization, we are improving about 9.1%. Okay, so we have less energy going to the mechanical brake, more energy go to the regen, and we save 9.1% as a whole. That brings me to the conclusion. So again, my message, as I said at the very beginning, is integration of real-time traffic and infrastructure information with vehicle control can offer significant opportunities for reducing transportation energy consumption. This has not been done historically. There was a good reason for that, okay? But I think now with the two new technology, connectivity, automation, we are at the time there is a good opportunity we can really integrate these two factors in transportation. A systematic framework which actually try to combine this under the so-called MPC model predictive control has been presented today. And we also show real-time implementation applied to 3 different powertrains, the conventional one with the engine and the hybrid electrical vehicle, as well as the electrical vehicle. We show you can get between 10 to 20% benefit depending on the traffic, depending on the type of powertrain. With that, I'll stop my presentation. Thank you.
Thanks, Sunny. We don't have any questions in the chat right now, so we can move on to Michael.
Thanks. I'll share my screen now. Can everyone see my presentation?
Yes.
Great. Awesome. So Sunny's spent a lot of time talking about the powertrain and the vehicle control level at the level of like individual speed and accelerations. And I want to talk about a different level of trying to reduce energy consumption and emissions, which is the route choice. I'm a associate professor in civil engineering. I've been studying route choice and its effects on traffic congestion for many years, since 2009. But specifically, what I want to focus on is the effects of route choice on emissions. So, I'd like this graphic to introduce what we are gaining by focusing on emissions transportation. This is from the EPA in 2022. They release a new graph like this every couple years or so, but the numbers don't change that much. The emissions from the USA, if we look at total greenhouse gas emissions, there's 28% coming from transportation. And if you look at the breakdown of transportation specifically, in terms of vehicles on the road, we have 57% from light duty vehicles and 23% from trucks. So there's a lot of opportunity to improve the total US greenhouse gas emissions by reducing emissions from transportation, and that's what we want to focus on, of course. To introduce why we can use route choice to reduce emissions, I think it's helpful to talk about the road power equation of what affects the power required for your vehicle to move along the road. And Sunny's been using this as well. And of course, this is just talking about the road power, not the influence of the powertrain on how you're getting that power. But if you just look at the power itself, that's really where congestion is going to have the effect. So looking at the total road power, it's split into four components, which is air resistance, rolling resistance, acceleration, and grade. And two of these get affected particularly by congestion. When you're driving in congestion on a arterial or on a freeway, you have a lot of frequent speed changes. And what happens with speed changes is that you have to spend energy accelerating, and a lot of that energy is often going to be lost when you have to brake to slow down, unless you have a really good regeneration system for a hybrid or electric vehicle. Another thing that happens is that the road power, of course, depends on how fast you're driving, but looking at the powertrain side, internal combustion engine vehicles, which are most of the vehicles on the road, are usually more efficient at higher speeds. So with congestion, there's kind of two impacts that result in congestion causing emissions to be higher relative to driving in lack of congestion. So in other words, emissions per mile driven will be higher. So in other words, we could conclude that route choice should affect your energy and emissions that you get as an individual driver. On the flip side, you might be thinking, okay, so we should change our route choices to affect the energy and emissions. And that's exactly what Google Maps started doing in 2021. Actually, if you wanted to open up your phone right now, you would see that there's an option that says on Google Maps, there's an option in the settings that says, do you want to Google Maps to give you routes for the minimum travel time or the minimum CO2 emissions? And by default, Google Maps is set to minimize your individual CO2 emissions, which is related to travel times, of course. Having a long travel time is, of course, going to increase your emissions, but it's not exactly the same. So right now, most people using Google Maps are probably not, unless they're particularly aware of this and changing their settings, they're probably going to be trying to minimize their individual carbon dioxide emissions instead of their individual travel time. Okay, great. But we end up having this question of, if you have, say, 40, 50% of the drivers that are trying to minimize their individual emissions, that's going to affect congestion patterns, right? The route choices of those drivers that are based on emissions are going to affect congestion patterns, which is going to affect the emissions that result from those route choices. And so the question here is that if you have 50% of drivers trying to minimize their individual emissions, how does that actually affect the total system emissions for all the vehicles? Both the vehicles that are trying to minimize their emissions and both the vehicle and other vehicles are trying to minimize their travel times. So we have this sort of feedback loop where the route choice, of course, affects your emissions, which affects route choice, but there's this equilibrium that forms as you go through this feedback of your emissions affects your route choice, but then the route choice affects the emissions of other vehicles. And it doesn't the goals of the drivers in trying to minimize their individual emissions don't align directly with the goal of our goal probably of trying to minimize the total system emissions. These are two different things and they can conflict in some examples. So I want to show that they do conflict. And before I show that, I want to go back to a classic example of looking at route choice and travel times because that one's easier to understand. So there's a very well-known concept from the 1950s called user equilibrium, which is the idea that when drivers choose routes to minimize their individual travel times, their route choices affect the travel times of other drivers, which and feedback affects the route choices of the drivers as well. So we want to find essentially user equilibrium, which are route choices where no driver can improve their travel times by changing routes. In other words, you're on the shortest route and there's no incentive for you to change. That's what we call user equilibrium. It's an equilibrium behavior, and that's true for everyone else. But it's not the same thing as minimizing traffic congestion. This is similar to emissions because instead of route choices and travel time having feedback when we're doing eco routing, we have route choice and emissions having a feedback loop. So let's spend a little bit of time looking at travel times for a moment. I want to review the well-known Brace paradox, which demonstrates the problems with individual travel time or user equilibrium behavior, which is what people are normally doing, which is minimizing their individual travel times. So I'm going to draw this simple network. It has 4 nodes, A, B, C, and D, and there are one-way roads connecting A to B, B to D, A to C, and C to D. The little functions you see are the travel time. So the travel time from A to B is x over 100, where x is the flow from A to B, the volume of cars. A to C and B to D, I gave those constant travel times, so in other words, no congestion there. And then C to D has a travel time of x over 200. If we look at 4,000 vehicles per hour traveling from A to D, the split that forms user equilibrium is to have 1,000 vehicles going on path A to B to D, and 3,000 vehicles going on path A to C to D. And the reason this is user equilibrium is because the travel times are equal. So in other words, there's no incentive for any of the drivers to switch paths because they would have the same travel time by switching paths. So the classic example is, let's say we have this network and we build a new road. So in other words, I'm going to build a road from B to C. And this road is going to have a travel time of 5, a constant travel time, which never gets congested. So then what happens to the user equilibrium behavior? Now, ideally, you're building a road, you would like the travel times for everyone to go down, right? That's why you build roads, is to make transportation better. But what ends up happening is there's this route choice shift where everyone starts to use the path A to B to C to D, which has 4,000 vehicles per hour, and that creates a travel time of 65 minutes because links A to B and C to D are going to get congested. So you might ask, well, why don't people use the other paths, A to B to D or A to C to D? And if we look at their travel times, path A to B to D has a 90-minute travel time due to the congestion on link A to B, and path A to C to D has a travel time 65 minutes due to congestion on link C to D, so no one's going to switch routes. They're all going to be on A to B to A, B, C, D because that's the fastest route they can find. What happens is that by building this link or changing, in other words, the route options for travelers, we now have everyone creating a lot of congestion on links A to B and C to D, and paradoxically, that makes the travel times for everyone, all drivers, increase because they're all trying to minimize individual travel times. So in other words, there's this well-known fact that building or improving a road can make traffic worse due to user equilibrium route choice. There have been a few examples, I think, in New York, Germany, and South Korea, where people observed this in practice. So of course, this is for travel times. I want to focus on emissions. We're going to see a similar effect there. Yeah, so here's a slide with the examples I found in New York, Germany, and South Korea. You can find you can look these up as well. It's basically the reverse situation where they removed a road and found that travel times went down by removing a road. So looking at this Brace paradox, this is saying if we build a road, we can actually increase travel time. And the reason that happens is because when you build a road, you're thinking of hopefully that road reducing the total system travel time or the traffic congestion. But when drivers choose to minimize their individual travel time, that's actually a different goal. It's a subtle difference, but it's a different goal, and that results in different route choice patterns. So we're going to see the same effect when we look at Google Maps. They're by choosing or by guiding people on routes to minimize their emissions, if we have enough people following Google Maps, we end up creating scenarios where, well, the goal of reducing individual emissions is different from the goal of reducing total system emissions, and these actually conflict. So in other words, when we try to minimize total system emissions, we really need to anticipate the effects of these route changes on emissions. If we just try to minimize individual emissions, we're not actually necessarily going to reduce our total system emissions at all. And so that's what I'm going to show you in the next few slides. We want to look at how well does individual vehicle eco-routing work. Now, to do that, we have to create some models of the emissions that people would use to choose their routes. And I've obtained some models from a paper in Transportation Research Part A from 2013, where they used the EPA's MOVE software, which is very well accepted in terms of predicting emissions, and they input the traffic model, a standard traffic model, and they ended up with these regression models for fuel consumption and emissions. These are interesting because they're monotone decreasing with speed. In other words, as congestion increases, the fuel consumption emissions will increase per mile increase, which is the pattern we would expect, as we saw a few slides ago. So what we're going to do is predict that drivers will choose routes to minimize either fuel consumption or emissions, and we want to see how that affects total fuel consumption and total emissions. So let's start off with a very simple network with just two links, link 1 and link 2. So drivers are going from A to B. There are 4,000 vehicles per hour going from A to B, and they have the choice of either two links. Now, what I was looking at is what happens if you vary the parameters of these links? And specifically, let's vary the length of link 2 and its free flow speed. So this is showing a graph. This graph shows on the x-axis the variations in link 2 length in miles and a link 2 free flow speed in terms of how fast people would drive if there's no congestion. The axis or the color coding here shows where total system emissions went up or where it went down. So of course we want it to go down. So the green shows that where the total system emissions went down. The red shows it going up. So you can see that when drivers are trying to minimize their emissions, they form a different route choice pattern, and it doesn't actually help that much relative to minimizing their travel time, which is what we would assume drivers would do before any eco-routing effects. The green areas are kind of small. That's where we see decreases in total emissions. The red areas are where we see increases in total emissions. There's not much green area in this graph. There's a lot of link parameters linked to free flow speeds and lengths where eco-routing actually just increases total emissions and is, in other words, bad. Why does this happen? It's because the route choice patterns create different congestion patterns, which cause different levels of emission. And I want to do this not just on a simple network, but also on larger networks. And to make this more realistic, I've also created examples where some of the drivers are eco-routing, some of the drivers are trying to minimize their travel time. So in other words, the route choices affect congestion or emissions, congestion affecting emissions, of course, and then those affect the route choices. In other words, what we want to do is find a mixed user equilibrium where it's a route choice solution where no driver can improve their goal by changing routes, and the goal of each driver could either be minimizing their travel time or minimizing their individual emissions. So I have several networks here. These are networks that are standard test networks, are publicly available, but they are fairly large, a lot larger than the previous toy example I created. And so the point of this is to show that the effect of eco-routing on various cities. So let's look at Eastern Massachusetts, for example, which is on the left here. As you can see, as the eco-routing proportion increases, the total emissions decreases slightly, and then it starts to increase again as the proportion of eco-routing vehicles passes 50%. Looking at the right network, Barcelona, we see that the total emissions is just mostly increasing with the proportion of eco-routing demand. So in other words, what's happening is that as we have a large number of people eco-routing, that affects the congestion patterns and it causes emissions to increase. Now, that's not true for every city. Winnipeg has the same pattern where increasing numbers of eco-routing vehicles increase emissions, but Chicago is the opposite pattern where as people start eco-routing, the emissions decreases. But hopefully this kind of demonstrates that it's not as simple as just trying to get people to minimize their individual emissions. We need to do something more complicated. And the fact that Google Maps is actually giving us routes to minimize individual emissions may not necessarily be good in every city. It may be increasing emissions in some cities. So that brings us to the question of how do we actually minimize total system emissions with route choices? Because indeed we can. So that's looking at that problem, we have to consider why it's difficult. If we try to choose routes to minimize total system emissions, we have to consider not just the impacts of routes on an individual vehicle's emissions, but we must consider impacts of route choices on congestion, which would affect the emissions of other vehicles. So in other words, if you change routes, if you decide to use, say, I-35 instead of Highway 88, you're now affecting congestion on I-35, which is going to affect the emissions of other vehicles using I-35. And if there are a lot of other vehicles on I-35, you've now possibly increased the emissions for other vehicles while reducing your own. So you have to consider those impacts when we want to minimize the total emissions and not just your own emissions. There are a couple other things that make this very difficult to solve, though. We don't really know future travel demand. In other words, there's a lot of uncertainty or stochasticity about when people want to travel and where they want to go. And if we're creating a planning model, we don't have to deal with that stochasticity. But if we're trying to route drivers as in Google Maps, we would, because Google Maps can't predict where people want to drive. What happens is as you pull out your phone, you ask for a route, and Google Maps has to give you a route. It doesn't know that in 5 minutes, someone else will want to drive to other places. So it can't plan for future traffic. The other problem that we run into is that the relationship between route choice and traffic congestion and emissions is actually very complex. And the models I showed before were simplified versions used for long-term planning. But if we want to reduce emissions on a day-to-day basis, we really need to use a more complex and realistic model. And these models exist, but they usually require simulation to solve, which makes it quite hard to solve optimization problems. So they're basically three algorithmic approaches that we might consider when Google Maps is asked for a route. How could we try to give the eco routing to minimize total system emissions? So the simplest one is a long-term planning approach, static traffic assignment model. It's a very simple traffic flow model. It's great for planning, still used. It doesn't really handle stochasticity and future travel demand, nor does it have a complex traffic relationships like queue spillback, traffic signals, things that do matter in the day-to-day behavior. We could go the next approach or the next extension is dynamic traffic assignment, which includes those complex traffic flow relationships, but it still does not have stochasticity. The other problem with dynamic traffic assignment is that optimizing it requires solving a very large optimization problem, and no one's actually managed to do that on any networks of reasonable size. So the third approach that includes both stochasticity and a complex traffic relationships is a Markov decision process model. We need a Markov decision process for stochasticity. It does model complex behavior, but it becomes even more difficult to solve in a traffic assignment. So keep that in mind that as we go through this, what I have is probably not the optimal solution, but we've done some mathematical work on getting something that seems to work pretty well. So I want to spend some time describing this model. There's a lot of math here, so I'm going to go briefly through it. I want to hit on the concepts of how we model this. So we need to track the movement of vehicles over time. And the way we track that is by looking at segments of roads, like the segment of a road between two intersections. If we look at how many vehicles are on that segment of road, changing over time, there's a conservation law. The number of vehicles at time t plus 1 is the number of vehicles at time t minus all the vehicles that exited plus all the vehicles that entered. So this graphic at the bottom kind of shows an illustration of what that would look like. If we look at link L, there are 3 incoming links where vehicles can enter and 3 outgoing links where vehicles could leave. And the number of vehicles on link L is by conservation, it stays the same unless vehicles exit or enter. We can also add intersection constraints to model whether vehicles are entering or exiting based on the proportion of vehicles that want to move from L to the next link, and then we can add further traffic signal constraints on this traffic flow model. So what that would look like, in other words, is we have this Markov decision process where we have a one-step transition between the number of vehicles on a link at time t and the number of vehicles on a link at time t plus 1. It's a one-step transition because it's based on the entering and exiting vehicles at that time point. There's stochasticity in terms of entering demand, which creates a stochastic transition. The control variable is actually our route choice. So if we look at the vehicles on link L, someone's going to decide which link they go to next. Do they go to link M1? Do they make a left turn? Do they go straight to go to link M2? Do they make a right turn to link M3? That's what we call eco-routing or whatever their out choice is. So that's what we're going to control. And we can control this at each time point. At each time the vehicle tries to leave a link, we can decide where they go, which is kind of akin or similar to Google Maps updating the shortest path in the middle of your drive based on updated information. The objective here, of course, is minimizing the total emissions, which you could write as a function of the traffic volumes on various links. It's just impossible to solve this computationally because there are just too many dimensions, so this runs into the well-known curse of dimensionality. So instead of trying to solve it computationally, we're going to derive an algorithm that has nice mathematical properties in terms of reducing emissions. So this builds on the max pressure approach, and the conceptual idea for max pressure is we want to choose a performance metric, and we're going to find a simple algorithm and then prove that our algorithm mathematically achieves that performance metric. So the typical metric used for these approaches is maximizing throughput. And the way you formulate that in terms of math is saying that the number of vehicles in a network remains bounded over time. What that means is that as vehicles are entering the network over time, people are departing their houses, they're departing parking garages, they're entering the network to drive somewhere. The number of vehicles in the network will increase as vehicles enter. So the only way to make this bounded is for vehicles to exit at the same rate at which they enter. So in other words, entering vehicles equals exiting vehicles on average, which achieves maximum throughput. Now, of course, we don't want maximum throughput here. What we really want is emissions. So I want to replace the idea of number of vehicles in the network being bounded with emissions in the network being bounded. So if we have vehicles accumulating in certain links or getting a lot of or certain links are becoming very congested, the emissions will become very large due to that. So we want to maintain boundedness. Now this is admittedly not the same thing as optimizing the total system emissions, but it does tend to work, as we'll see. So what that looks like is for the max pressure algorithm, is we want to solve an optimization problem to determine where people should drive. This looks like a kind of nasty optimization problem. It's actually quite easy to solve. But what it's really doing is computing these weight functions, which is basically the difference between queues at queues approaching an intersection versus queues at the far end of an intersection. In other words, we want to move vehicles from long queues to short queues, or from areas of large emissions to areas of smaller emissions to get vehicles out of congested areas. The rest of this is just various constraints on those movements. Um, we can do some mathematics to simplify this control policy. The main point here is that this algorithm is very easily to parallelize. In other words, we can compute this per intersection, per destination, which makes this possible to run in real time, unlike some of the other optimization approaches, which would involve solving very large optimization problems requiring many hours. So this is something we could do in real time. Why does it work? Well, we can get some mathematical properties. So first off, let's define a set of demands, D, which is a set of demands that could be stabilized by any route choice policy. So we're talking about travel time routes, minimizing through or maximizing throughput or minimizing congestion. You can think of many different route choices. Um, there's a set of demands where if you look at the best route choice, the set of demands is the set of demands D is a set of demands that we could serve from any route choice. And if our demand is not in the set, it's impossible to stabilize the network in terms of keeping emissions bounded. What we do achieve, though, is that if our demand is in the interior of the set, then we can ensure stability. In other words, the total emissions or the average emissions in the network will remain bounded, which is kind of nice. It's saying that our emissions won't blow up. In other words, where route choice will try to avoid emissions being large from congested links. There are some mathematical reasons why this might work. So first off, we need to achieve maximum throughput to maintain stable emissions, and that kind of justifies the max pressure approach. If we don't have maximum throughput, what that means is vehicles are accumulating in the network, causing congestion, and that congestion is increasing over time, which is resulting in emissions. The other implications of this sort of control algorithm is that emissions will tend to be lower than alternative route guidance algorithms is because we're trying to maintain bounded emissions and not let them not like congestion emissions go off to infinity. This differs from individual eco-routing because there's no guarantee that when everyone's trying to minimize their own emissions, it's going to cause some congestion patterns. There's no guarantee on how those congestion patterns affect the emissions or throughput over the overall network. And in fact, I'm sure we've seen situations where trying to minimize your own travel times creates large congestion on freeways or in other areas that are definitely making emissions worse. So in theory, this should be better than individual eco-routing, but of course we need to try this out on a network. So we've worked on this Bologna network. We simulated it using the micro simulation Sumo. So by micro simulation, I mean that it's modeling the individual car following behavior for all the vehicles here. There are 45,000 vehicles here, so it takes quite a bit of time to run the simulation. We have to simulate the vehicles and then also calculate the route choices of the vehicles periodically. Here's the kind of the baseline that we're benefits that we're seeing. So we have on one hand the baseline here, the baseline column here shows vehicles choosing routes to minimize their own travel times. The controlled is, of course, our own eco-routing control to minimize whole system emissions. And we're seeing benefits that CO2 is like 6.57%. Depending on which type of emissions we look at, it could be from 5 to 8.5%. What this shows is that we can be effective at reducing our emissions. But actually, what's really interesting is that if we, instead of picking these baseline conditions, let's look at different possible numbers of trips. So the x-axis here is showing how much demand we have on this network, which ranges from 1 times to 5 times of our baseline demand. And the y-axis is the reduction in emissions. So this y-axis is numbered 0, -2, -4, etc. So in other words, a higher value on the y-axis indicates a larger reduction in emissions. So looking at the CO2 and fuel, that's the red and green line here, we can get over 10% reductions in emissions. Looking at the hydrocarbon, which is the bright green, you can get 13% reductions. But of course, the the effect depends on the network. So if we have a very low demand, we're not going to see much benefit from eco-routing because there's just not much congestion and there's no congestion to avoid from route choices. Now, if we see a very high demand, the benefits start to decrease as well because there's just congestion everywhere. And again, it's really hard to avoid congestion with route choice if there's congestion everywhere. So our best thing occurs when there's a high demand, not like the highest demand, but at some point in the demand scale, you're going to see a peak of what our eco routing can do, which is over 10% reductions in emissions. Now, of course, there are probably more opportunities to improve this. This is unlikely to be optimal, but 10% reduction in emissions is a good starting point. So to wrap this up with some conclusions, the main takeaways are that when we're eco-routing to minimize individual emissions like we are with Google Maps right now, that can actually increase total system emissions due to changes in congestion patterns. I saw we created several examples of networks where it does in fact increase total system emissions. And particularly there are larger networks where increasing the proportion of vehicles using eco-routing, so like over 50%, the eco-routing vehicles change congestion patterns in such a way that emissions became worse. It doesn't happen on every network, but the fact that it does happen means that we should spend more time scrutinizing whether eco-routing is a good idea on particular cities. For example, I don't know whether it's a good idea in Minneapolis, St. Paul or not, but we do know that Google Maps is using eco-routing in Minneapolis and St. Paul. And it's not clear whether it's increasing or decreasing our total emissions. Now, if we want to decrease total emissions, there are ways to formulate the problem and develop algorithms. We created one algorithm that could be run in real time that gives route guidance that tends to reduce the total system emissions. It does handle stochasticity in terms of not knowing future travel demand, and it also has a realistic traffic flow model. We have numerical results in a detailed simulation, which is probably the standard of simulations in terms of predicting traffic congestion and emissions. So it's possible to reduce our emissions. We just need to make sure we're studying that to reduce it and using algorithms to reduce total system emissions. So I want to give a thank you to a couple of students that contributed a lot to this research: Rocio Okada Antunes and Mauro Zamanpour. And of course, I want to thank CTS for funding part of this research. So that's the end of my presentation. Happy to take questions too.
Thank you. Thank you very much, Professor Levin. Ross, do you see any questions on the chat or clarifications for Professor Levin?
Yeah, let's move into questions. So we have 4 questions in the chat right now. I'll get to those in the order they were received. And if we could bring Songchuan back. Okay, you're back. Good. If you have questions, you can always raise your hand and we can unmute you at the time, or feel free to put those additional questions in the box. All right, so our first question is from Wei Ming, and the question is, many electric vehicles now have energy recovery functions. What impact will this have on optimization?
Well, the energy recovery, I assume, is the regenerative braking I talk about. Yeah, so basically means that, unlike conventional vehicle, when you slow down, you do not have to use mechanical brakes to dissipate the kinetic energy that the vehicle carries. Instead, you use a generator to exert torque on the vehicle to slow down the vehicle, and the electricity generated in the process is being charged back into the battery. In fact, in my chart, I show with optimization, you aggregate more regen, okay, therefore save more energy.
Thank you. It's fun to have these 2 presentations side by side. Definitely, you can see it in the questions. People are asking both about the vehicle and the environment and all the choices. We're all particles in this flow from time to time, so it's fun to have the particles talking about the flow. Our next question is from Steve. are users actually choosing routes based on emissions? I would assume this would be the most energy efficient route for ICE, electric, or no, internal combustion engines, or is it travel time?
Yeah, so right now, Google Maps by default is giving routes based on minimizing total CO2 emissions. So of course, not everyone's using Google Maps. A lot of times you drive to work and we're using our kind of our own knowledge of the route. But also a lot of people are using Google Maps now that it's integrated into cars. A lot of people, like, I'll just open Google Maps and ask it what route I should take because I don't know the congestion each day. So a lot of people are using eco routing right now, and so there's kind of a mixture. We'd say some people are using eco routing, some people travel time routing.
And you said the default was this eco routing, so they may be using it even when they don't understand they are.
Exactly.
Well, let's follow up on that one and take these a little bit out of order. You seem to be putting an issue in front of Google here. Are they aware of the potential adverse effects of this and their response?
Yeah. I I'm not sure if they're aware or not. So I actually wrote a research proposal to Google on this exact problem. I did share some of these results that I showed today. I didn't get a response from them. I sent this proposal in a couple of times, so I'm not sure how much they're actually aware of this. I haven't really been able to get into contact with anyone from Google. Whether they have plans to make use of the real-time traffic data to inform the design of system optimal routing application, I would say probably not because there really aren't many of of these algorithms out there. Like if they wanted to create a system optimal routing application, they would run into the problem of what algorithm to use. And since none really exist, they probably wouldn't be able to do that.
All right. Yep. That question was from Michael. So now we'll circle back to the question from Jason in the chat. Mike, one, do you consider vehicle age and engine size? Um, they lack, they affect emission levels. And two, do you consider mixed traffic with both conventional vehicles and EVs?
Yeah, so for the first question, yes. The way we did our emissions was that we were either using regression models from EPA's MOVE software, which of course considers vehicle age, engine size, as well as penalties for like more engine warm-ups. And when we did these simulations in Sumo, that also used the standard emissions model, which included those as well. For part two, we did not consider electric vehicles in our model at this point. Most vehicles on roads are internal combustion engine. It was just easier to focus on those. I mean, certainly there's nothing stopping us from considering electric vehicles, just hasn't been done.
For the next one, I'll insert my own question here. So if folks want to connect with your research, aside from watching this presentation again, how can they access the present or the underlying studies that both of you have talked about?
Yeah, so the first part of my talk, which was looking at the effects of individual eco routing on toll system emissions, that's been published in IEEE Transactions on Intelligent Transportation Systems. The second part of research is new. It hopefully will get published at some point, but it's still in progress. And for Sunny,
Yeah, the work I presented all have been published. So, people should be able to find them on our website. Of course, they're more than welcome to contact us.
All right. Well, thanks for the links and the preview of new research to come there. All right, the next question is from John. Did your models take into account the types of congestion? Basically, full loaded semis, taking longer to accelerate, or requiring high bridge clearances or turn radiuses, some of the specifics about the geometry of both the vehicle and the roads.
that's really interesting. I think when we were doing our simulations, it was all passenger cars. And there are definitely ways to simulate trucks and the turn geometries. I think this is still in progress. And of course, in an initial work in system optimal equal routing, so we weren't considering all these variables, which of course would affect things. I don't see any reason why um, the effects of trucks or buses on congestion wouldn't be like. I think we could incorporate them into our model. It just hasn't been done yet.
Nice. My next question is, so this one's for Michael. When you did the one on Bologna, and you got to that result where the slide had like maybe 4 times traffic and about a 10% that maximum peak reduction in emissions. Did you look into like the links in the nodes? So this is from someone on the city side asking, because we have noticed some changes in traffic patterns. Instead of the common roads that people know the best, we see a lot more traffic on the maybe not common roads and kind of creative cut throughs that the algorithm might be creating. What was happening in the network on that optimized solution that users might be surprised about?
Well, we definitely saw changes in congestion patterns, places where there used to be long queues of vehicles and the queues were shorter. Um, I don't know the network well enough, and I didn't look into the details to know if users were on, say, smaller roads or roads that they would be surprised by. I mean, there are definitely route choices happening. It's just hard for me to say if it was something that would be surprising or bothersome.
All right, and now we have another question coming in. Feel free to keep entering those in chat. Remember, you can raise your hand as well. So this one's from Jason. It seems like your analysis is based on Google users. What percentage of drivers use Google, particularly for commuting? Because it's not based on all users. How would it affect the outcome?
Yeah, that's a great question. I'm not actually sure. It's not easy to figure out how many drivers are using Google and how many of those drivers are using eco routing. I'm not aware of Google publishing information on what percent of their users use eco routing. The other issue, of course, is that even if someone is using Google Maps, we don't always follow it directly. Like we might say, I don't think it's right, so we might choose one of the alternate routes that it has. So it's really hard to know like how many people are actually using their eco-routing model. As I said, it is the default route model, so probably a lot of users are using the eco-routing model. But of course, there's Apple Maps and other options. Um, in terms of modeling this, some of the when I looked at the city networks, I was looking at different proportions of vehicles choosing eco routing. So like some vehicles doing eco routing, some doing travel time routing, and looking at how that proportion affected total system emissions. So definitely if we have a large proportion of vehicles using eco routing, that's going to have a larger impact on congestion patterns. And so it's more likely if we have like 50% of eco routing that we're going to see emissions increase rather than if you have like 5% of vehicles eco-routing, we're likely to see small decreases because they're not going to have a big impact on congestion.
All right, we got our first raised hand. It looks like Maurizio wants to get in with a question.
Thank you. Professor Levin, can we assume that if someone is using the eco-routing function of Google Maps, if they don't see any congestion, can we assume that it is in fact more less carbon intensive?
It's hard to say because you're saying if they're using eco routing and they don't see congestion that it has less emissions. It's hard to say because the route choice that leads to less congestion might have more miles, right? It's like if you take a longer route that has less congestion, your emissions will go up because it's longer, but your emissions will go down because of less congestion. So there are two competing effects. It's hard to say which one will win out there.
We still have a couple minutes. I got one for Professor Sun. So we don't have access to the optimization technology that you spoke of, but the user behavior is one thing that we can control. After you've gone deep on this study, what advice do you have for just the drivers to help their own efficiency before the technology can take over?
Yeah, Ross, that's a good question. In fact, before I answer your question, maybe I was listening to the question that went to Michael. A lot of I would say 80% of the question went to Michael is about what kind of vehicles, as well as how do you ensure people, like the map, everybody use the map? How would that affect? It's about, at the system level, how do you actually implement this kind of technology? It's not an easy thing, obviously. But I guess I was listening, I was thinking there is a difference here. If you bring technology such as connectivity and automation into individual vehicles, if you actually have enough market penetration, many of the things that were asked will be solved automatically. Okay, because we will have more and more influence on how the vehicle will behave rather than leave this to many individual people who use this, who use that, who has this preference, who has that preference. But because at the end, everybody benefit. That's the point, right? I mean, everybody benefits. It's not like I just benefit. So I just want to emphasize the point that and that can be done as part of the vehicle design and manufacturing. Okay, so and that is transparent to the driver. I mean, so that's basically is technology going to the vehicle, which can be connected to the system technology, as Michael talked about. Back to your question, Ross. We saw, I drive every day to the university. You saw people, I actually think that the good driver behavior, in fact, integrate both safety and efficiency, right? So because you try to avoid a sudden acceleration and deceleration, you try to keep reasonable distance from other cars. Therefore, you also improve safety as well, because we have snows here. And in general, they tend to reduce energy consumption as well, because back to the question Michael was saying, we have to remember one thing. It wasn't just the travel time. It wasn't just the distance. It is even for the same travel distance. If you travel at a higher speed, the wind resistance, the wind that your car gets is proportional to the speed. Sorry, is proportional to the square of the speed, V square. Okay, and the power, that's a force, the wind blowing at you. Okay, the force that you see from the wind is a proportion to the square of your speed. Then the power is a cubic to your speed. So if you simply travel that fast, you actually consuming more energy, even you are the only car on the road. Again, you will travel faster for sure. I mean, you will get point A to point B faster, but you are using more energy. I mean, there is no simple way to trade off. That time saving is energy here. My point that is, all of those, if when you put them together, individual people, I think people consider safety, consider energy, consider emissions, which is benefit for themselves, also for others. But I see that if we bring more technology automatically into the vehicle at an affordable cost, it will benefit everybody.
Well, I'm going to give you the last word, Professor Sun. Thank you for your presentations today, Professors Sun and Levin. The last several minutes here, we're going to open it up to our participants. Thank you all for the great questions you had and for attending today. If you have any events or issues that are in this area that your organizations are facing, we invite you now to either place them in the chat or raise your hands. Maurizio and I are always collecting these issues, and we would also invite you to reach out to us if one comes to mind as your. So this is our round robin section and invitation to kind of connect with the CTS Environment and Energy Group. As I mentioned, CTS has a website where you can review all of the studies. You can find their YouTube channel on there and review past presentations and webinars. And this call for any other organizational challenges or issues remains open. So keep Maurizio and I up to speed if you see any of these places where energy and environment comes together and challenges in your work. We're always looking for those research ideas. Maurizio, I'll turn it back to you since we're not seeing anyone step forth.
Well,
Or
I
close
just
out.
would like to really thank Michael and Song Xuan for speaking today. This was a great presentation, something that we don't talk and we don't think enough about. It's just this optimization of the network. We're always thinking about electric to reduce emissions or, transit, but optimization is like a really important issue that we should be talking more now with all the data and resources that we have. So I really want to thank you and thank you everyone for coming. This has been a great webinar and hope to see you next time. Thank you, Russ.
Thank you all.
Thank you.